Okay, though. All right, so today is going to be mainly on transformations. I'm going to start by kind of defining a few, not really new things, but new ways of looking at things. Look at coordinate frames so that we can kind of work in arbitrary coordinate frames rather than always in the same global coordinate system. Set up coordinate frames that we can then set up as transformations. We're going to look at new ways of writing down our coordinates, just new notation for our coordinates, in order to be able to use these coordinates frames set up as matrices to then transform our coordinates in the kind of most clear and most efficient manner that we can. So, to begin with, I want to look at what we call homogeneous coordinates. So, make sure I can read this properly on the screen as well. So, homogeneous coordinates. And to begin with, I'm just going to kind of put them forth, this idea of homogeneous coordinates. And then as we start looking at coordinate frames and how we use them with matrices, we can see why we set our coordinates up this way for our calculations, number one, and how we can differentiate better between vectors and points by doing it this way. So, where before we have a point P which has the coordinates px and py. Let's just do it in 2 dimensions first. I'm now going to say we have the point P, which is a column matrix, a 1 by 3 column matrix in 2 dimensions, which has the coordinates px, py, and 1. I also have the vector v, which has the coordinates vx and vy. But I'm going to say for my calculations, I want to set it up, define it this way. V is again a 1 by 3 column matrix, vx, vy, and 0. So my rule right now is simply, if I have a point, I'm going to set it up as a column matrix, but I'm going to add a 1 at the bottom. If I have a vector, I'm going to do the same thing, but I'm going to add a 0 instead of a 1. So let's leave it at that for now. In 3 dimensions, you just take a different color and write the 3D version. You can say in 3 dimensions, I have the point px, py, pz, and that'll give me a 1 by 4 column matrix, px, py, pz, and 1. And my vector vx, vy, vz will be the vector vx, vy, vz, and 0. So in this case, the only thing that we kind of have now at this point is that I don't have to tell you that these coordinates are a vector and these are a point. To put up coordinates 2, 3, I don't have to explain whether it's a point or a vector. I can simply say, if we have these coordinates for a calculation, this is a point. If there's, however, a 0 at the bottom here, it's a vector. So that's the only thing we gain to begin with. But we'll see how this actually affects the calculations in a way that the calculations work out for points and vectors differently, exactly in the manner that we've defined already. Things that can and can't be done for points, and things that can and can't be done for vectors. All right, so let's leave homogeneous coordinates here for a while. And let's look at another thing, which is, coordinate frames. Coordinate frames. I'm just going to draw this in 2 dimensions, but like with the other, which you can just add the 3rd dimension and the same things apply. It's just hard to draw in 3 dimensions. So if I draw the usual coordinate system that we've been drawing, I simply say I have these axes here. I have the x-axis and I have the y-axis. And these are basically these 1-dimensional kind of number lines here. And I count along them. They're rulers, basically. So I have the x-axis, which is a horizontal ruler. I have the y-axis, which is a vertical ruler. So this is my coordinate system. What I want to do with coordinate frames, I want to say I want to be able to set up an arbitrary coordinate frame, or an arbitrary coordinate system. A coordinate system that starts somewhere other than 0, 0, which is this point. And it might even be rotated or oriented in a way so that when I count along my x coordinates, I'm not actually counting horizontally. It may also be scaled in a way that when I'm counting along my axis, I'm not always going exactly 1 unit at a time in my coordinates. So I want to be able to set up this arbitrary coordinate system such that I'm just going to say I have my kind of point of origin here, and then I have a vector A, and I have a vector B. And I'm going to say this is my coordinate frame. And if I want to draw something into this coordinate frame, I want to be able to say the point 1, 1 in this coordinate frame is here. This is the point 1, 1 in this coordinate frame. It'd actually be nice to change the colors a little bit here and say this coordinate frame I'm drawing in red. I hope it shows properly. So I have the vector A, I have the vector B, and this particular point here, which doesn't really matter in which color the point is, but the coordinates for this point are 1, 1 in this coordinate frame, right? Let's just draw the coordinate frame in red as well. So in this coordinate frame, I start at the point of origin and I count 1 in this direction and 1 in this direction. So I'm counting along A and I'm counting along B for my x and y coordinates. So then the question is, if A and B and the point of origin are defined in my global coordinate system, which I've drawn here, what would be, if I draw now in black, I want to draw the coordinates for this same point, but the coordinate that it has in the global coordinate system, the point 1, 1 in this local coordinate frame here. Can you see how I could calculate this for any arbitrary coordinate frame?
1 plus that mark x.
Okay. So
With x coordinate and y coordinate 1 plus that mark y coordinate.
okay. So we have the point of origin here, and we take that x coordinate and we add what to it? Add 1.
Yeah, the 1 over there.
Do we not have to take this 1 here and apply something to it? Because if I take this coordinate here, let's say I'm going to take my point of origin plus 1, 1, which is my point here. I'm going to take the point of origin, and then I'm counting 1 in this coordinate frame, right?
No,
or in this coordinate system. So I'd go here to 1 and here to 1.
So that frame has other units.
Yeah, so this frame, when I take the x coordinate of my point that is defined within this coordinate frame, I want to go along its x-axis, so to speak. And its x-axis is defined by the vector A.
Don't you need to know how much is scaled then?
Well, that would be kind of inherent in the vector A, and the coordinates of the vector A.
unit vector. Okay.
It might be unit vector. It might not necessarily be a unit vector. If I want to scale something that I draw into this, I might actually want to have it a different vector. So what I want to do is I'm not going to split this. For this particular point, 1, 1, I would say this is the point of origin plus A plus B. Right? So I'm the point of origin, and then I translate this point by A. I move it to here. I say this point plus A is a new point, which is as if I moved this by exactly A. Then I take that point and I move it by exactly B up to here. So this same point has the coordinates 1, 1 in this coordinate frame.
Given that A and B have both the same length.
Not necessarily. So if I change the length of B and say this is now my coordinate frame, then this is the point 1, 1 in the red coordinate frame. If you feel my explanations are not hitting home with you, we can take as much time as we need just to kind of little by little figure out this idea. So here I have the point 1, 1 in this completely skewed coordinate system here. In fact, this doesn't even have to be 90 degrees. But to begin with, I just like to draw this as kind of same length vectors with 90 degrees between them, but that's not even a necessity. So in this coordinate frame, my local coordinate frame, this point is now 1, 1. But the same point in the global coordinate frame is the point of origin plus A plus B, which is actually plus 1 times A plus 1 times B. So if we take this and make it more general and say, let's just erase this for now, and say I'm gonna, well no, let's take one more kind of specific again. Let's say I go 1, 2 along A, and then 1/2 of B. And say this is again the point 2, 0.5. You see this is 2 and 0.5. That same point in the global coordinate system is then my point of origin plus 2 times A plus 1/2 times B. I basically add 2 A's to here, I add 1/2 of B, and then I go to here. Does this make sense? So a lot of what we're doing at this point, it's not complicated math as such. It's just I need to get across why we're doing this and what the idea is. And right now, my kind of goal is to say, if I define something as simple as 2 and 0.5 within this arbitrary coordinate frame, I want a method to be able to give these coordinates in my local coordinate frame, but then calculate these coordinates, which are the coordinates for the same point. It's the same position, it's just the same position defined in another coordinate system. The reason why we want this, if it's not clear already, it will be as we move along through transformations. So same point, different coordinate system. So the general case here would be if we can say
Global coordinates equals that formula.
yeah. So with transformations, we're always thinking about, especially in classic linear algebra, we're always thinking, I'm taking one point and I'm changing it to another point. That's my transformation. I'm taking it to somewhere. So I'll use that notation here, and I'll say, this is my point P. And this here is my point Q. But what I kind of want to get across from the start is that P and Q are the same point. but I have the coordinates p, which are the coordinates for this point in the local coordinate frame. Q is the coordinates for that same point in the global coordinate frame. So Q here equals this. The general case would be if P equals x, y, and I'll do it in 3 dimensions here, since this is the general case, and I'm not going to draw it specifically. If P equals x, y, z, then Q equals what?
Are you assuming they are unit vectors? A and B?
No.
No.
I'm not assuming anything about A and B, in fact. I'm just assuming they're vectors.
We'll have that symbol plus. Oh, sorry.
Sorry?
The origin
Yeah, the origin.
plus x times. What are we working in 3 dimensions?
Yeah, okay. Let's, in 3 dimensions, let's just add the kind of z-axis here. And let's then add to this the vector c being our 3rd dimension.
Then x times a, y times x times a plus y times b plus c times z.
Yeah.
Plus a.
Will it be px times a?
Yes. Okay, let's. It's nicer that way, that's true. Let's have these coordinates px, py, and pz so that it's clearer here what we're working with. Either way, px times the vector a plus py times b plus pz times c. So I basically say I'm going to scale the vector a by the x-coordinate, and then I'm going to add that to the point of origin, which is basically, I start at the point of origin, I say how many vectors a am I going to do, that is what is my x-coordinate, what is my first coordinate. If that's 2, as in this case, I count 1 vector a, 2 vectors a. So I'm moving within this coordinate frame. So 1, 2 here. Then I add to that the vector b scaled by the y-coordinate. So how many vectors b am I going to go? Which is just like in a regular coordinate system. I say if I have the coordinates 2, 0.5, I go 2 along the x-axis and then 1/2 along the y-axis. I'm just going along a different vector. And finally, I take the last coordinates and I multiply that with a vector c, and I add that to the whole. So I've gone x-coordinate many vectors a, y-coordinate many vectors b, and z-coordinate many vectors c. So this is the general case here, where our coordinate frame is the point of origin, the vector a, the vector b, and the vector c. See. All right, let's just leave this in 2 dimensions then here. All right, this is fine. If we go from, well, we'll just draw this up later and kind of see this when we have proper transformations. I'm going to take this now, take the image out, and draw this general case up with the points and vectors as homogeneous coordinates. So we can say the coordinates qx, qy, qz, and 1 equal the point of origin x, the point of origin y, point of origin z, and 1, plus px times ax, AY, AZ, sorry, 0 plus PX times PY, PX, BY, BZ, 0. So this is the vector B plus PZ times the vector CX, CY, CZ, 0. All right, so this is what it looks like just writing this up here. But then I could also say, well, I can just write this as one column matrix where each of the values in this column matrix is basically a calculation. So, say, so this is one column matrix here. So we have Bx plus Px times Ax plus Py times By plus Pz times Cx. Sorry, Px times this, Px times this, Px times this, Py, Py, Py. Can anyone see a resemblance to calculations that you've done before? Similar, yeah. Lots of stuff. We have these three kind of linear combinations here. But something you've done in another course. So I could set this up. Let's just use the last line here. How can I set this up as a function of Px, Py, Pz, and 1? Like, can I set this up as a matrix multiplication? And what's happening? There's some number times Px plus some number times Py plus some number times Pz. And that's going to be the top of this column matrix here. So what number times Px? If we do a matrix multiplication here. So A times Px, sorry, Ax, we have Bx here, we have Cx here, and then finally we add to it something times 1, which is the point of origin, x. Then we have Ay, we have Az, we have By, we have Bz, we have Cy, we have Cz, we have the point of origin y, we have the point of origin z. And what would the bottom be?
0, 0, 0, 1.
Fair enough. Is this just a jumble of numbers and things to everyone, or does it make any sense as calculations? I'm going to open the window a little bit. It's
Why is it 0, 0, 0, 1?
here. You can see that Px is multiplied by 0. So in the end, what we want to get out is a point. It's Qx, Qy, Qz, and 1.
Okay.
And you can see that 1 will be multiplied with 1. The rest will kind of disappear with the zeros. So this 1 will be left here as a 1. So it's going to be a point. I'm transforming the point the point P with this matrix to give me the point Q. This may be a little bit of a complex way to get to this matrix. So let's dissect the matrix itself a little bit. What have we got here from our original kind of arbitrary coordinate frame? We've got the vector A, we've got the vector B, we've got the vector C, and we've got the point of origin. So our matrix our transformation matrix here is basically our coordinate frame, this arbitrary coordinate frame that we set up, and we said I have some point of origin in this coordinate frame, and I have some vector A here, I have some vector B here, I have some vector C here. Now these are the 3 dimensions. And if I want to set up coordinates P, which are kind of counted in this arbitrary coordinate frame, but I want to be able to calculate what coordinates that point has in the global coordinate system. The reason for this is, in computer graphics, we often want to take models that have been designed and built kind of with a 0.0 just in the center of the model. You say, I'm gonna have a computer game with a car in it. And the first thing you do is you tell an artist to draw that car. Then you get the model of the car. The artist just put his 0.0 in the middle of the car, right? But you want to draw 3 of these cars, all driving around in a big game world, right? So you can't draw each of them with its center in 0.0. And you also don't want to recalculate every single point into a new model before you then draw it. Instead, you want to say, I want this to happen. I need to recalculate every point so that it's in a different location. But I want to set up this transformation in a way that OpenGL can just know the car that I'm drawing now has a point of origin in, XYZ, somewhere out in the world. And it's oriented in a way that the vectors that define its orientation are these A, B, and C vectors. And we can manipulate those through rotations and through scalings. And once I've set up a matrix like this, I want OpenGL to be able to take the original points that the artist put in its model, where the center of its universe is the center of my arbitrary coordinate frame. That is, it has its own center of the universe, which is in its center. But I want to draw it, wherever I put my coordinate frame. Right now, my global coordinate system is here, but this car isn't supposed to be drawn here. I want to say I'm going to set up a transformation that is positioned here and oriented like this, so that my car will instead be drawn here. Then, once I've drawn all the points in this car, I want to say I want to draw another one, except now I want my coordinate frame to be positioned here, but oriented like this, and I want this to be a little bit of a bigger car. So I scale my coordinate frame as well. And then I draw the exact same car with the exact same set of points P, which were originally made by the artist. So I send the exact same points in again. The only difference is the transformation matrix that I apply to them, which will make the car be drawn in a completely different location and with a completely different orientation. So that's the idea behind these coordinate frames. I want to set up a new location and a new orientation for the model that I'm going to draw, and I want it automatically to be moved or to be transformed to that location as I'm drawing it. Then I want to set up a new location and a new orientation, and then I want to send another model or the same model again and get a new version of it drawn in a different place in a different location. Okay, so that's the idea. These are sort of the calculations. Now let's go to a clean board to be able to look at small examples here. So if we start with the coordinate frame again here, and we can say we have some kind of default point of origin here, which is 0, 0, and we have these default vectors A and B, which are just the vector 1, 0 and the vector 0, 1. Let's just do this in 3D from the start. Here. So something like this. And so we have the vector here. So this is 0, 1, 0, 1, 0. This is 1, 0, 0. This vector here is 0, 0, 1. And then we have the point of origin, which is 0, 0, 0. This vector, in fact, is called I. This vector here is called J. And this vector here is called K. So we might use those in some formulas and definitions
The
that we
zero
use.
point is called K, and the other one is called K.
No, sorry. The third vector is called K. Sorry. This point is just 0, 0, 0. What would a transformation matrix look like for the coordinate frame that just has I, J, and K as its vectors and the point 0, 0, 0 as its point of origin?
1, 0, 0, 0.
So we'd have 1, 0, 0, 0, 0, 1, 0, 0. I actually like to draw it usually this way because we're kind of thinking of the vector here. So this is the first vector, 1, 0, 0, and 0 because it's a vector, 0, 1, 0, and 0 because it's a vector, 0, 1, 0, 0, 0, but this is a point. This is the point of origin, so it ends up with a 1. So in linear algebra, this is what's called, can anyone remember? An identity matrix. Thank you. So the identity matrix is also a neutral transformation. It's a transformation that transforms coordinates back into themselves, which means it's a neutral transformation or basically a transformation for our base coordinate system, a coordinate frame that just lines up exactly with our base coordinate system. So what we want to be able to do here is we want to be able to put kind of simple transformations into this matrix here. So the matrix on the other side with AX, BX, CX and all that just looks like a huge jumble. Right now we're going to simplify it and we're going to say, what if I simply want to change the point of origin? If I want to make a new coordinate frame that has a new point of origin here, let's just call it P in this case, P, but I still want its vectors to be I, J, and K. But the point of origin is P. What would its transformation matrix look like?
Meaning just the scaling.
Just the translation. So I just want to translate, I just want to move, I just want to slithera.
When you just the identity matrix with the pluses.
So with the position, where would that come? Where would we put? So P is Px, Py, Pz. So where would that be put into? Yes.
You just put Px, Py, and Pz in the last column.
So yeah, in the fourth column here, Px, Py, Pz, and 1. Don't really have to change the color of the 1, it's the same. Okay, so here we have a translation. Translation, slitheren in Icelandic. A translation by XYZ means simply we change these parts of the matrix. You can also see that if we apply this to any coordinates XYZ here, any point XYZ, what are we going to get out? What will that result be? Yeah. X plus px will come here. We'll get 1 times x, 0 times y, 0 times z, and 1 times px. We'll get y plus py. We'll get z plus pz. And we'll get 1 times 1. Okay, so the coordinates will simply be translated. What do you expect to get if I apply this to a vector? So you can see it from the math.
A vector from 0 to translation.
You get a vector. I mean,
I will get a vector.
you get the same vector.
I get the same vector as I originally had. So we can see that 1 times x, 0 times y, 0 times z, and 0 times px. So the math gives us, yes, x again, y again, z again, and finally 0, 0, 0, and 0 times 1. So it gives us another vector that has 0 here as well, but nothing changed. So okay, we can see that the math does that, but conceptually, is that what we were expecting? By translating a vector, moving a vector from one place to another.
No, I expect it to have changed.
Do you expect it to have changed?
Oh no, it's
Like when we defined vectors and points, we said points have a position. They have an absolute position, and that's what their coordinate means. A vector, however, is a size or a force or a motion. Does it matter where I position this force? If I try to take this force and I say this force is now applied here, I'm now going to take the same force and apply it here. Did the size or orientation of the force change?
no.
No. And the vector is just the size and orientation. A vector doesn't have a position. So suddenly this idea of a vector just arbitrarily having a 0 here and a point having a 1, it suddenly makes the calculations work out as well. That is, a point can be translated. Also, if we just look at our arbitrary coordinate frame here, we have this coordinate frame here. If I draw a point here in this coordinate frame, which has in that coordinate frame the coordinates 1 and 1/2, we expect to get a different result for this coordinate system. This is something like 1, 2, 3, 4. Oh, could you use the other color then? Same point, but coordinates 4 and 1, 2, 3, just about. Let's imagine that's exact. Same point, different coordinates. Coordinates in my local coordinate frame, coordinates in my global coordinate system. If, however, I draw this vector here, and I want to say what are the coordinates for this same vector in this coordinate frame, if a translation was the only thing that changed. Yeah, okay, sorry. Obviously, it was supposed to be the exact same size, so let's leave it at that and say this is 1, 2, 3, 2. Good enough. Either way, different coordinates for the point. The vector drawn in each coordinate system, it shouldn't matter. I can draw this same vector here as well. It has the same coordinates, right? So okay, this is what I wanted. A translation does affect a point, a translation doesn't affect a vector. By using my homogeneous coordinates to put an arbitrary 0 here for a vector, 1 for a point, this happens. A vector isn't translated, a vector has the same force in any coordinate system. Should I continue or should I erase and let's leave it up, at least for now. So let's look at another idea. So let's make another identity matrix here. And now let's look at the idea of only scaling the vectors. I'm saying this is my new vector A here. It has the same direction as I, but it's twice as long. Let's just put some other scale on B here. This is my vector B. It has the same direction as J, but it's 3 times as long. Here's my vector C. It has the same direction as the vector K, but it's 1.8 times longer.
1.8.
Just about.
Okay.
It doesn't matter. These are arbitrary things. I'm not going to write actual absolute numbers here. But in the image, it's just about 1.8 times as long. Either way, the question is, let's say that A is Sx as long as I. So A equals Sx times I. B is Sy times longer than J. Make sense? So it's just J scaled by the number, the arbitrary number Sy, which in this case is 3. So right in this image, that's 3. In this image, this is 2. And C here, C equals the scaling factor Z times K. And the scaling factor Z is, in this case, 1.8. How do I change this transformation matrix so that it represents this scaled coordinate frame?
Multiply by the vector like above, but instead of x, y, z, you just do the s, y, s, x.
Okay, but can I multiply this with a vector?
And then you end up with a vector.
Then I end up with a vector. I want a new matrix.
I come up with a vector.
Not as such. I want to make this matrix as such that any vector that's multiplied with it will have this scaling added to it.
You multiply the ones then by the.
Okay, so basically my vector A, that used to be I, which is 1, 0, 0, is now Sx times as long. So that vector would be Sx, 0, 0. The kind of y coordinates here, the B vector, is Sy as long. So this is the y scaling factor. And here I have the z scaling factor. So here we have a scaling matrix. Scaling, or skölun, if you want to keep the Icelandic term. So what happens now if I multiply this with a point? X, Y, Z, and 1. And so to begin with, let's just look at this and imagine what is it that the concept was. Our concept was that if I take the coordinates x, y, and z, I'm going to start at the point of origin, which is still 0, 0, 0. We have that here, 0, 0, 0. Then I'm going to take the x coordinates and I'm going to multiply them with the vector a. So I'm going to count x times in this direction. So if I set up the point 2, 1, 0, let's say, I would go 2 times this vector, which leaves me at 4 now, right? Because this vector is 2 times as long. Then I'm going to go 1 times b, which still takes me up to 3 here. And then I'm going to go 0 times c. So the vector that is 2, 1, 0 will be here, 1, 2, 1. But in this coordinate frame, it should be 1, 2, 3, 4, and 3, 4, 3, 0. Okay, so this is kind of the effect. If I draw a point into a scaled coordinate frame, I'm counting by the scaled vectors. I'm not counting 1, 2, 3 here in the original coordinate system. I'm counting by the scaled vectors. So what do we expect to see here?
Sx plus x, Sy plus y.
Okay, Sx plus x times x with scaling, Sy times y. So we can see the math as well. Sx times x, 0, 0, 0, 0, Sy times y, 0, 0, 0, 0. So Sz times z, and 1. What do we expect to happen if we send a vector in here? Will the scaling of a coordinate frame affect a vector? Yes, no, yes, yes. So the translation, the position doesn't affect it. But scaling a coordinate frame, yes, that affects the motions, and that affects the sizes, and that affects the powers. So we basically get this exact same effect from scaling a vector as from scaling a point. Now the question is, how do we do, well, let's take a short break. Jo.
Skrifa EU explicitly.
Já, segja identity matrix er bara fylgið I, J, K.
Það er bara eins og að gera áhættinu. Þú láta það verði áhættinu.
Já,
Það er minna áhættinu.
Nei, það er ekki, ég gerði það bara minni.
Nei, I get ekki verið hér, því að I er vektor. I er vektorinn 1, 0, 0.
Já, það.
Þannig að I get ekki verið hér. I er allt þetta. Þetta er allt saman I.
Já.
Og þetta er allt saman J.
Þú myndir merkja á sig með EU káskilur. Var það ekki vitlaust ef maður er að mynda sig á það?
Það er allt í lagi, en það er þá bara merking þannig séð. Það hefur enga raunverulega merkingu, enga þýðingu í stærðfræðinni.
Það er ekki svona. Þau taka bara merkja eins og að gera fyrst.
Já. Já. Jú, í rauninni, þú veist. 0,0,0. 0,1.
Þetta er svona.
Þú getur gert eitthvað svona en... Ég er ekki það vel að mér í öllum möguleikum í framsetningu og fylgjum í stærðfræði og svoleiðis. Ég veit ekki alveg hvað er löglegt og hvað ekki. Þú máttu vera 1 eða 2. Skiptir ekki máli.
Og svo bara gefur nokkuð fleiri að gera nokkuð aftrykk. Þú veist.
Það er mjög einfaldlega að gera það svona.
Það er ekki flókið að það er svona eitt.
Hvað gerði ég? Ég gerði það ekki. 6.
Já, já. Já, jú, það var það.
Nej, det är
All right. Let's at least kind of begin again while people are coming in from the break. So what we're gonna look at here is what happens if we want to do both of these, if we want to both scale and translate. If we want our coordinate frame to represent both a new position and a new size, so to speak. Number one, how can we combine these transformations, and what is the effect that we're looking for in that case? I'm going to erase this, put up a clear image, a less cluttered image. Say, I set up a coordinate frame here, and I have a point P here somewhere. So I want my coordinate frame to start here in the point P, but I also want these vectors here, A, B, and C, to be bigger. So in this case, how could we combine these just within the matrices? Can I just put the Sx, Sy, and Sc here, and I'll get this result? I can, in this case. What if I want to kind of tell you what I want to do in words and say I first want to scale this coordinate system or this coordinate frame, and I then want to translate it? Where do I expect it to end up? If we say my coordinate system is here now, or my coordinate frame is here, I first want to scale it so that my coordinate frame is here. And now I want to translate it to, let's say, the point 2, 2. Where will its point of origin end up in the image? Will it end up here? 1, 2, 1, 2? Or is there another place that it could end up? If I say I'm first going to scale it by, let's just leave this in 2 dimensions here and say I'm going to scale it by 3, 2. So this is my scaling here, 3, 2. This vector scaled by 3, this vector scaled by 2. And then I want to add a translation, 2, 2, 1, 0, 1, like so. Is this the new point of origin? Like, what do my words even mean? I want to scale it first and I want to translate it then. Like, what do I have to take into consideration when I just say I want to translate it now? Like, is there a question you need to ask me to get clearer information about what it is that I want? Can anyone think of that question? Yes?
You want to translate it in what coordinate system?
Exactly. In which coordinate system do I want to translate it? Do I want to translate it in my coordinate frame, my local coordinate frame, which I have now scaled? Or do I want to translate it within my original coordinate system, which is still unchanged? And now it just starts depending on what I want to do, and also it depends on whether I'm doing classic linear algebra or if I'm doing computer graphics, what my answer is. So my answer now, doing computer graphics, will be, if I first scale this and then I translate, it will have to translate within the scaled coordinate system. So it will in fact end up with a point of origin here. That's the point of origin that I want. And this has to do with kind of how transformations stack up in graphics. Now I can go into a certain transformation and then back away from it and then continue going into it. These things have to happen in this order. Every single transformation that you add, you have to think of it as happening within the current coordinate frame. Classic linear algebra would think this differently. They would say, we're not transforming a coordinate system constantly. The coordinate system is always the same. We're transforming a point. So we take the point and we scale it first. And that scale here will mean that the point 2, 2 do we scale first or translate first? The scale of the point 2, 2, yeah, that'll take it up to here, 6 here, and then the translation by 2, 2. Am I thinking this wrong now? Now I've gone and confused myself here. So, no, we talked about scaling first, right? Yeah.
Yeah.
And it's, yeah, okay. And I was thinking about a different point. What was the point that we're going to set up? We hadn't even said what point we were going to draw there, right? So let's imagine we're going to draw the point 0, 0. That'll mean that the point 0, 0 will be scaled not at all, and then the point 0, 0 will be taken up to here. So in the end, the point 0, 0 will end up here in this classic linear algebra sense. In computer graphics, however, we're going to say we don't really scale the point. We first scale and then translate the coordinate system that it's in. So that coordinate system has gone to here. And then we draw the point 0, 0 in the point of origin of this new translated and scaled coordinate system. Okay, let's imagine we're taking two arbitrary, well, let's just look at these matrices here. What can we do to them to get these results? Okay, I can multiply these two matrices together. I'm going to take this up for a bit. I'm going to say, what happens if I multiply 1, 0, 0 px, 0 y, z, 0, 0, 0, 1 times sx, sy, sz, 0, 0, 0, 1. What result will I get here? And what result will I get if I do it the other way around? Sx, 0, 0, 0, 1. And here 1, 0, 0, dx, 0, 1, 0, dy, 0, 0, 1, z. Okay, so what's going to be the difference between these results?
One is going to shift first and then transform, and the other is going to transform and then shift.
Okay, so one's going to shift first and then transform, the other one's going to do it the other way around. In computer graphics, these would be kind of flipped to what it's in classic linear algebra. So let's just look at the results first. Just saying this one is translated first and then scaled can have a different meaning. So we need to do the math because that never has a different meaning. So so this is sx, 0, 0, 0. So we're going to get sx here, we're going to get 0 here and 0 here. In the end, it's going to look like this, 0 sz, 0, 1. The question is what we get here. So we get 0, 0, 0, and 1 times px. 0, 0, 0, 1 times py. 0, 0, 0, 1 times pz. In the other case, we're going to again end up with these parts here, the same. 0, sy, z, 0, 0, 0, 1. The difference is here we're going to get sx times px. 0, 0, 0, 0, sy times py. So the scaling in this case is affecting the point of origin as well. So here the scaling is affecting the point of origin as well. So this is where we said in computer graphics this would be I scaled first and then I translated, because the translation then happened within the scaled coordinate frame. So I said I scaled first, then I translated. Who here has taken linear algebra? And did you learn that when you want to combine two transformations, where you do one first and the other one afterwards, then you multiply them in reverse order? Is this something that you've heard?
Like into the function, if I remember correctly.
Sorry?
So think of like a composition function.
Yeah. So we can say if transformation 2 is applied to transformation 1, which is applied to a point, and we can say that transformation 1 is matrix 1 times the point, and transformation 2 is matrix 2 times this, then we can simply use matrix multiplication rules and say this is the same as first multiplying matrix 2 with matrix 1, getting kind of one matrix here, and multiplying that with P. So I'm kind of telling you we're going to do it the other way around. So I'm going to say classic linear algebra tells us we take whatever we say happens later and multiply that first. The difference, and this is always a tricky one to explain, maybe I'm just bad at explaining it. The difference is really not in the mathematics, they're still the same. The difference is what we view as happening first and what we view as happening second. Or that is, what are we applying these transformations to? So in computer graphics, we're transforming the coordinate frame itself. And when we add a new transformation, we're transforming it within its current within its kind of current state. We're saying if we've already scaled it, then all transformations that are applied after that will apply in a scaled sense. They'll apply scaled. So if we, I think we've kind of gone through this already. In computer graphics, I say if I scale this, make it bigger, and then translate it, I'm translating it within this coordinate frame. And then when I draw a point, let's say now I've got the coordinate frame that has been scaled 2, 2, and I draw the point 1, 1, it ends up here, which in this coordinate system here would be, so if this is the vector 2, 0, this is the vector 0, 2. We scaled it first, then we translated it by 2, 2, which then makes this 4, 4. And then I draw the point 1, 1. 1, 1 in this coordinate frame, which will have the coordinates 6, 6 in kind of a global coordinate system. And I said this happened because I scaled first and translated next. Let's do the same things in a different order. And I'm going to say, I'm first going to translate to 2, 2. Then I'm going to scale this coordinate system. And scaling a coordinate system within itself, or a coordinate frame in computer graphics, means I scale it, it looks like this now, I scale it from its own point of origin. Which means I scale it from here, it doesn't affect the position of it. I translated it first, then I scaled it, and I scaled it just from where I put it. So then I draw the point 1, 1, which gives me the point 4, 4. Now in computer graphics, I said, this means that in this case, I translated first and then scaled. Here, however, I scaled first and then I translated, so I translated within this coordinate system. I could just as well have said, well, all of my transformations happen in the original coordinate frame, meaning that if I just say I scaled first, which means I get this size here, then I translate it, my translation is happening in the global coordinate system, so I end up here. If, however, I translate first, and I say, okay, I translate to here, which gives me this coordinate frame, then I scale this coordinate frame. Classic linear algebra would say if you scale this coordinate frame, you're scaling it from here. You're scaling it from the global coordinate system, meaning you end up growing the entire image from here rather than from here. So it's still just 2 coordinate frames, and we still get them from the exact same math, from the exact same calculations. It's just about how we look at it. So I hope I haven't confused you too much here, in order just to say the classic linear algebra sense of saying an added transformation. So if I have some matrix and I want to add another transformation, I want to take a simple transformation and add to my current transformation. Classic linear algebra would say multiply the added one to this side. Computer graphics would say multiply it to this side. It doesn't change the math, really. What it changes is just how we're looking at our transformation. And the reason we want to do this way in computer graphics is that if I've already taken, let's say I've translated to somewhere because I want to draw the car model there. I've translated to here. I've oriented with some rotations my coordinate frame so that my car is oriented in this way. And then I draw the whole thing. Then I look at it and I feel the car is a little bit too small. In classic linear algebra, that would mean I'd have to go way right to the beginning, right? I'd have to start with a scale, and then that scale would affect everything that I do from then on, and I'd have to update all of my kind of calculations, my scalings, my rotations, and everything based on that original scale. In computer graphics, instead we say we're not scaling, or if I do it the other way around and end up with scaling, classic linear algebra would make that scale not only change the size of the car, it would make it change everything from kind of the center of the universe. So it would scale everything out from there. Is this making sense? What we want to do is that if I have positioned the place I'm going to draw this car here, I've oriented and sized, or I've oriented this, and the car looks exactly to be in the right place that I want it to be. When I add a scale, I want it to happen in exactly the correct place. I already have all the mechanisms in my game to make the car drive at the correct speed, end up at the correct location, orient itself correctly. The only thing I want is to make it a little bit bigger. So I don't want this scale to happen from here and affect everything and change everything about my car. The only thing I want to change is its size here locally. So that's the reason we want each added transformation to affect the local coordinate frame, but we want it to affect it within the local coordinate frame, not within the global coordinate system, but just within the local coordinate frame. So any scaling will happen from the center of the local coordinate frame. Any rotation will happen around the center of the coordinate frame. That's another thing with classic linear algebra. It says if I have a point that's here, and I've translated it, or started here, and I've translated it to here. Now I rotate this point. I rotate it around the center. Again, if I've already found the position for my car, and I have this coordinate frame, and I want to rotate it, I don't want it to rotate like this, right? I don't want it to also change its position. I just want it to rotate within itself. And this is the effect that we get from applying our added transformations to the right side of our original transformation. I feel like I've made this super confusing. However, let's continue here a little bit with rotations, and then we can maybe, yes.
So in computer graphics, you would always end by doing the translation. Start by scaling and orienting.
No. In fact, I think usually I'd start with the translation because if the translation is just to the correct point, kind of in the world, I know where it's positioned in the world, I want to first translate to there. Then I would rotate, or scale, it usually doesn't matter. Usually I'd rotate next, and finally I'd scale in order for the scaling not to affect the rotation if it's a skewed scale, if it's different on the axes. If I were to scale first, I would make my coordinate frame bigger. If I translate after that, that translation would happen within this coordinate frame, which means it would happen in a kind of in a coordinate system that I've lost control of, in a sense.
So you always start by translating.
Usually start by translating, then rotate, then scale. If that's the only things you need to do.
Is there a preference to rotate or scale before either, or?
I would say rotate first, but it doesn't matter except in the case where the scale is different on the axes. If I have a scale that's 3 on the x-axis and 2 on the y-axis, I've scaled this kind of in a skewed way, then the rotation will become weird. And this could rotate in a way that the axes don't have 90 degrees angles anymore. So usually I would translate first, then rotate, then scale, if it's only those three things you're going to do. I'd like to look at it in a program. I doubt we have time for it today, but in the session on Monday, look a little bit at it in a program, how we can kind of add up translations and then back up a little and continue in order to do things like solar systems or drawing modular objects, drawing a car and then drawing its tires and then kind of going back and drawing things within things. Let's look at rotation. I think there's no specific reason kind of to go through a lot of math behind the rotation. But in 2 dimensions, basically if I want to take my coordinate system and I want to rotate it counterclockwise by the angle theta, so that my original coordinate frame is here, my new coordinate frame is rotated, then the transformation matrix that does that is cosine of theta minus sine theta 0, sine theta, cosine theta 0, 0, 0, 1. Okay, so this is the rotation. If we want to add a rotation, like I said, if we want to add a rotation after a translation, like in the case where I want to draw the car somewhere, I want to put it where it should be. So add a translation. It's here. Then I want to orient it in the way that it's spinning. So then I add the translation. And in computer graphics, the rotation, sorry. I want that rotation to happen around this point, not around this point. And so we can see, if I take something that already has a translation, let's just put it here, something that already has a translation, 1, 0, let's say px 0, 1, Py, 0, 0, 1. What we get here is the cosine up here, and then 0 and 0. We get the minus sign up here, 0 and 0, and we get px. No, we get 0, 0, and px here. Minus sign px. We get sine theta, cosine theta, and py, 0, 0, 1. So here we're saying I translated first, then I rotated. I rotated within my local coordinate frame. This second transformation I added to the right. Classic linear algebra, however, would have said you actually didn't translate first and rotate second. What you did was you rotated first here, and then you translated, but not within this coordinate frame, but you translated within the global coordinate system and ended up with this same coordinate frame. If I do it the other way around, this would be 0, 0, cos minus sine, sine, cos, px, py. The difference here lies in the last line again, and that now suddenly we get cos theta times px minus sine theta times py. So suddenly the rotation is affecting the translation as well. Sine theta times px plus cos theta times py. And 1. So if we look at the math is always the same. So this yields a particular matrix. In classic linear algebra, they would say, well, what you did was you translated first, which means we translated to here, and we got this particular transformation matrix, or this particular coordinate frame here. Then you rotated, but you rotated around this point, and you ended up here. So took the rotation here, and so you ended up with this coordinate frame, because you translated first, and you rotated around the center, which is what classic linear algebra always does. It does things as relative to the center of the main coordinate system. But in computer graphics, I'd say I didn't. I actually rotated first. I rotated, and what I got was first this coordinate frame here, then I translated. But seeing as my local coordinate frame is like this, I'm not translating 1, 2, 3, 1, 2 here. I'm translating 1, 2, 3. I should have gone higher here. 1, 2, 3, 1, 2 here, and ending up at the same place. Am I making sense? Again, the results, there are simply two results. One of those results is this coordinate frame. The other result is this coordinate frame. The difference is how I think it. Do I say, I translated to here first, and then I rotated within this coordinate frame, as I do in computer graphics, because every added transformation has an effect within my current coordinate frame, as relative to my current coordinate frame. So computer graphics would say I end up with this by translating first, then rotating. Whereas translating first, then rotating would end up here in classic linear algebra. But in computer graphics, I'd say if I rotate first and then translate, I'm translating by these vectors, 1, 2, 3, 1, 2, and I end up here. Classic linear algebra would say, you end up in the same place, but I'd call it rotating first, then translating. No, sorry, translating first to here, then rotating the whole thing. These things make a lot of sense to me. Maybe I've just made things complicated for you. That's okay. Final rule is we add, so if I have a matrix that has some transformation, and I want to add transformation T add, and my current transformation is calculated with M, and I want to add the transformation T add, which is calculated in M add with M add. Then I'll say the combined transformation which is T combined, equals M times M add. So I add to the right side. Because I'm not transforming points within the global coordinate system, I'm transforming coordinate frames. I'm transforming coordinate frames as relative to their current state. Are there questions regarding this? I can simplify this again and take a few. Or let's look at...
Isn't it called translation, not transformation?
Transformation is kind of the general term for everything we're doing. Scaling is a transformation. Rotation is a transformation. Translation is a transformation. Translation as such is just the moving thing from one location to another. Rotation is rotating, obviously. Scaling is kind of multiplying the size of vectors and objects. Let's look a little bit at rotations in 3 dimensions. Just so that we've looked at that, so we can kind of start working with it when we have our computers. So in 2 dimensions, a rotation obviously is happening here. I have this vector, I rotate it by this angle, and I get this vector. I'll make this bigger. I have a vector, I rotate it by an angle, and I have a new vector. When I go into 3 dimensions, and I say I want to rotate a vector by an angle, again, what's an extra question that you need to ask me to actually know what I'm asking for? What more do you need to know than I want to rotate, and I want to rotate by this angle? Even if I say I want to rotate counterclockwise.
What axis?
Yeah, like about what axis do I want to rotate? So do I want to rotate, if I have this vector, do I want to rotate it like this? Do I want to rotate it like this? Do I want to rotate it, I've got this axis, I've got this axis, well, do I want to rotate it like this? Just about itself? If we try to take this particular rotation and expand it to 3 dimensions, what vector am I rotating about, or what axis am I rotating about in the two-dimensional rotation? This is my 2-dimensional rotation. I'm going to draw now a big 3-dimensional coordinate system. The rotation that happens in the whiteboard, what axis am I rotating about?
Z.
So I'm rotating around z-axis. That would mean z-axis is kind of pointing straight out here. So rotating around the z-axis in a 3-dimensional coordinate system would be the same as just plain old rotating in 2 dimensions. So then I can say let's take all this out. I just have to make it a 3-dimensional transformation matrix. And I'm going to say this is rotation about x-axis, no, z-axis by theta degrees, or by the angle theta. Doesn't matter if it's degrees or radians. So this is rotation about the x-axis. how can we imagine that a rotation about the x-axis would look? Like we're rotating about the z-axis. What does that tell us about, for instance, the z-coordinates of everything that we affect?
Unchanged.
Okay, z-coordinates are unchanged. If this is the model that I'm rotating here, I'm rotating it around the z-axis. It's not moving further from the board, it's not moving closer to the board. That is my z-dimension. The z-dimension is not changing. It's just rotating around here. Fine. How can we see it in this matrix multiplication? That two things. The z-coordinates are not changed, and what else can we say about this matrix here? Not only that they are not changed themselves, but they also do not affect the change of anything else. So we have the third column, we have the third row, both of which are just as in an identity matrix, telling us that neither are the z-coordinates affected, nor do they affect the result. Can anyone see which is which? Does the column tell me that the z-coordinates are not affected?
Third column.
Which is the row and which is the column?
Like column goes down, row goes horizontal.
Yeah. So this is the column, this is the row. If I want to know whether a certain matrix will affect...
Is it the row?
So the row is what will affect the z-coordinates. The column tells me whether the z-coordinates affect the calculations. So the row tells me whether the z-coordinates are affected, that is, if something happens to the new z-coordinates. A row like this will mean that the z-coordinates will simply be unchanged, no matter what else happens. A column like this will tell me the z-coordinates of whatever point I multiply it with this will have no effect on the result. All right, in this case, both. Z-coordinates don't have an effect, z-coordinates aren't affected. So what will that tell me if I want to do a rotation about the x-axis by the angle theta?
Then you 1, 0, 0, 0.
Okay, I can pretty much say that the first row and the first column will probably be like this.
Then you do sin minus, cos minus sin.
Then I do cosine minus sine, 0,
And then sine.
sine, cosine. All right, let's add the angle in here, theta, 0, 0, 0, 1. Okay, so when we're rotating around the x-axis, we're basically rotating like this, rotating out of the blackboard like so. The x-axis or the x-coordinates of everything have no effect on this. It's just happening in the y-z plane. How about a y-axis rotation? It's going to be happening like this, around this axis. Say rotation about the y-axis by the angle theta.
Just do the same thing again.
Okay, do the same thing again, except now it's the second row and the second column. So if we want to make sure that this is counterclockwise, this has the same rotation direction relative to the axis that we're rotating about, which is y. There's only kind of one thing we need to wonder about, and that's where does the minus go?
Setup.
So we have cosine here. No, wait. cosine here, and cosine here. Sine here, minus sine here. It'll just affect the direction of the rotation. So it's still a rotation about the y-axis, whether we have the minus here or here. But it should be here in order for it to be the same rotation direction based on the vector that we're rotating around. So it's counterclockwise. When the vector is pointing at us, it'll be counterclockwise. We can view this kind of as a circular buffer. So if we're moving this from here, we move it from here, move it down to here, where does the minus sign here end up? It's kind of gone off the side, so we just flip it back in here. Cosine has gone off both sides, so it goes up here. This sign has gone off the bottom, so it goes up here. One way of looking at it. So all of these can be combined. Again, as always, I've taken a little bit more time going through all this than I meant to, but that just means that we have plenty of time on Monday to do examples. I can do examples in the computer, I can do examples on the whiteboard, and we're gonna really start kind of looking at transformations there, but also on Monday you can have assistance with the 2D game assignments, mainly in the second half of the class, which will be kind of open assistance, and Benny will be there again to assist you with the assignment. But we're going to look a little bit at transformations in the program and how we can work with those and kind of expand on these ideas and make them a little bit more hands-on rather than just numbers on a whiteboard. So if there are no questions, then have a nice weekend.
Yeah.